In the first fraction of a second after the universe began, matter and antimatter should have annihilated each other completely, leaving nothing behind but light and silence, and an empty cosmos with no stars, no planets, no one to wonder why. And yet, somehow, a small imbalance occurred, a tiny asymmetry that physics still cannot fully explain. And from that unexplained remainder came everything that exists, including the body resting here now, including the breath moving gently in and out. If this channel has become a quiet place to return to, subscribing means these stories will continue to find their way to you. The atoms in your hands, in your chest, in the soft tissue of your mind, asking these questions, all of it inherited from that single impossible surplus, that matter which should not have survived, and did. Here is how it happened. As you lie here now, in this quiet moment, your chest rises and falls with each breath, and there is nothing you need to do about that. The breath arrives on its own, as it has been arriving since the very first moment of your life, and it will continue without any effort from you at all. You can simply notice it if you like, or let it fade into the background of your awareness, because either way, the air moves gently in and out, carrying with it tiny particles that have traveled an unimaginably long way to reach you here, in this room, on this particular evening. Each breath you take contains atoms, and those atoms are older than the earth itself. They are older than the sun. They are, in fact, older than most of the stars you might see if you were to look up at the night sky. Though, of course, you are not looking at anything right now, because your eyes may already be closed, or closing, and that is perfectly fine. The atoms do not require your attention. They simply are, and they have been for a very long time, and they will continue to be for a very long time after this night has passed into morning and then into memory. The human body contains roughly 7 octillion atoms, which is a number so large that it resists any ordinary understanding. Written out, it would be a 7 followed by 27 zeros, a figure that stretches across the page like a long, quiet sentence with many commas. 7 octillion atoms make up the whole of you, from the soft tissue of your brain to the gentle curve of your earlobes, from the delicate bones of your inner ear to the approximately 2 square meters of skin that holds everything together. Each of these atoms has a history, and that history reaches back to the earliest ages of the universe, long before there were planets or oceans or anything that might be called life. Carl Sagan, the American astronomer who spoke so gently about the cosmos, once wrote in his 1973 book, The Cosmic Connection, that we are made of star stuff. He meant this quite literally, not as a metaphor or a piece of poetic license, but as a straightforward description of physical reality. The atoms that compose your body were forged in the cores of stars that lived and died long before our own sun began to shine. And this is simply what happened, in the same way that rain falls or seasons change. There is nothing mystical about it, though it may feel that way sometimes, lying here in the dark with your breath moving softly in and out. The calcium in your bones, for instance, came from dying stars. Calcium is element 20 on the periodic table, and it requires a great deal of energy to produce the kind of energy that only exists in the final stages of a massive star's life, when such a star exhausts its fuel and begins to collapse under its own gravity. The temperatures and pressures at its core become extraordinary. And in those extreme conditions, lighter elements are fused together to form heavier ones. The calcium that now gives your skeleton its strength was created in just such a moment, in a star that no longer exists, in a region of space that may now be empty or may contain new stars that have no knowledge of their predecessor. The iron in your blood has an even more specific origin. Most of the iron in the universe, including the iron that allows your blood to carry oxygen from your lungs to your tissues, was produced in a particular type of stellar explosion called a Type Ia supernova. These events occur when a white dwarf star, which is the dense remnant of a star that has already died once, accumulates enough material from a companion star to trigger a runaway nuclear reaction. The explosion that follows is remarkably consistent in its brightness and its composition, and it produces vast quantities of iron and nickel, which are then scattered across space to eventually become part of new stars, new planets, and new living things. The iron in your blood was manufactured in such an explosion billions of years ago, and it reached you by a path so long and so improbable that it hardly bears thinking about, especially at this hour. The scientific understanding of how elements are formed inside stars was first comprehensively described in a paper published in 1957 in a journal called Reviews of Modern Physics. The paper was written by 4 scientists: Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle, and it is often referred to by the shorthand B²FH, pronounced B²FH, which is simply the first letters of their surnames arranged in a way that is easy to remember. This paper, which ran to over 100 pages, carefully mapped out the nuclear processes by which stars transform hydrogen and helium into all the heavier elements, from carbon and oxygen to gold and uranium. It was a monumental work of synthesis and calculation, and it provided the foundation for our modern understanding of stellar nucleosynthesis, which is the technical term for the way that stars build atoms inside themselves and then release those atoms into the universe when they die. Before the B² paper, the origin of the elements was not well understood. Scientists knew that stars were made mostly of hydrogen and helium, and they knew that heavier elements existed on Earth and in meteorites, but the connection between these facts was not clear. The 4 authors of the 1957 paper drew that connection with meticulous care, showing exactly which nuclear reactions were responsible for which elements, and under what conditions those reactions would occur. It was, in its way, a kind of genealogy of matter, tracing the ancestry of every atom in your body back to the nuclear furnaces of ancient stars. And like all genealogies, it revealed connections that might otherwise have remained hidden, links between your present existence and events that took place long before anyone was alive to witness them. Now, as you lie here with your eyes closed or nearly closed, breathing steadily in and out, there is something else worth knowing. Something that makes your presence here even more remarkable than the simple fact of your stellar ancestry. According to the most precise theories of physics, the matter that makes up your body should not exist at all. The universe, according to these theories, should be empty of matter, filled only with light and energy, with no atoms and no stars and no planets and no people lying in bed listening to someone talk about the origins of the elements. This is not a dramatic overstatement or a piece of rhetorical exaggeration. It is simply what the equations predict, when they are solved carefully and completely. The reason for this prediction has to do with the symmetry between matter and antimatter, which is one of the deepest and most puzzling features of the physical laws that govern our universe. For every type of particle that exists, there is a corresponding antiparticle which has the same mass but opposite charge. When a particle meets its antiparticle, they annihilate each other, converting their mass into pure energy in the form of light. The laws of physics, as we understand them, treat matter and antimatter almost perfectly symmetrically, which means that the early universe should have produced equal amounts of both. And if equal amounts had been produced, all of the matter and all of the antimatter would have annihilated each other within the first few moments after the Big Bang, leaving behind a universe filled with nothing but light. No atoms, no molecules, no stars, no planets, no people. And yet, here you are. Here is the Earth, and the Sun, and all the galaxies that fill the observable universe. Somehow, for reasons that physicists do not yet fully understand, the early universe produced slightly more matter than antimatter. The imbalance was tiny, perhaps one extra particle of matter for every billion particle-antiparticle pairs, but it was enough. The matter and antimatter annihilated each other almost completely, but that tiny excess of matter remained, and from that excess came everything. Every atom in your body is part of that surplus, that slight asymmetry that the equations did not predict. You are made of matter that, according to our best understanding of physics, should not be here. This is not a problem that has been solved. It is an open question in physics, one of the most profound open questions there is. Scientists have various ideas about what might have caused the asymmetry, various proposed mechanisms that might explain why the early universe favored matter over antimatter, but none of these ideas has been confirmed. The mystery remains, quietly, in the background of all our investigations, a reminder that even our most successful theories are incomplete. The universe is here, you are here, and the equations say it should not be so. This is simply the state of our knowledge, and there is something almost restful about admitting it, about acknowledging that some questions do not yet have answers, and may not have answers for a very long time. In 1995, the Hubble Space Telescope was pointed at a small, apparently empty patch of sky, a region where very few stars were visible and where there seemed to be nothing of particular interest. The telescope was held in that position for 10 consecutive days, collecting light from that tiny section of the heavens, and when the resulting image was processed and released, it showed something extraordinary. That small patch of sky, which from Earth appeared to be about the size of a grain of sand held at arm's length, contained approximately 3,000 galaxies. Not stars, but galaxies, each one containing hundreds of billions of stars of its own. The image, which came to be known as the Hubble Deep Field, revealed that the universe is far more densely populated with galaxies than anyone had previously imagined, that even in the darkest and most empty-seeming regions of the sky, there are vast collections of stars too distant to see without the most powerful instruments. All of those galaxies are made of matter, the same matter that should not exist, the same matter that makes up your body as you lie here now. The iron in those distant stars is the same element as the iron in your blood, produced by the same nuclear processes, governed by the same physical laws. The calcium in alien worlds orbiting alien suns is the same calcium that gives your bones their strength. There is a continuity to the material universe, a sameness that stretches across all of space and all of time, and you are part of it. You are not separate from the cosmos, looking at it from the outside. You are made of the same stuff, assembled in a particular pattern that happens to be conscious and alive and capable of wondering about its own origins. And so you lie here, breathing gently, with 7 octillion atoms holding their places inside you, each one older than the Earth, each one forged in a stellar furnace that burned out long ago. The calcium in your bones remembers the death of a star, though not in any way that could be called memory. The iron in your blood carries traces of an ancient explosion, though not in any way that could be called carrying. These are just the physical facts of your existence, the ordinary circumstances of being made of matter in a universe where matter is, by all theoretical accounts, improbable. You are here anyway. The atoms are here anyway. The galaxies in that grain of sand patch of sky are here anyway. All of it impossibly present, all of it quietly existing in defiance of the symmetries that should have erased it. There is nothing you need to do with this information. You do not need to feel awed or grateful or small or significant. You can simply let it settle around you like a blanket, like the warmth of your own breath returning to you with each exhale. The facts will still be true in the morning, and they will still be true on nights when you do not think about them at all. The atoms will go on being ancient. The stars will go on fusing lighter elements into heavier ones, and the mystery of why there is something rather than nothing will go on being a mystery. For now, you can rest in the gentle company of these facts, letting them become as familiar and as unremarkable as the rise and fall of your own chest, as the soft weight of your body against the bed, as the quiet hum of the universe going about its business while you drift toward sleep. Let us begin. Then, at the very beginning, or at least as close to the beginning as our mathematics will allow us to venture, which is, it must be said, remarkably close indeed, though not quite all the way, for there remains a tiny sliver of time at the universe's birth that resists our understanding, a gossamer curtain drawn across the first instant that even our most sophisticated equations cannot part. And so we will start just beyond that curtain, in the earliest moments that physics can describe, and we will walk through those moments slowly, as one might walk through a garden in the early morning, noticing each small thing, each transformation, each quiet miracle of emergence. The physicist Steven Weinberg wrote a small book in 1977 called The First 3 Minutes, and in it he traced, with the patience of a cartographer mapping newly discovered terrain, the opening chapter of cosmic history, the brief overture during which the universe established the conditions that would eventually, after billions of years of patient expansion and cooling and collapse and reformation, lead to everything we see around us now, including, it should be noted, you yourself, listening to these words, made of atoms that were sketched into existence during those very first minutes. though they would not become proper atoms for some time yet, and would not find their way into a living creature for billions of years after that. We begin at what is called the Planck time, which is 10 to the power of negative 43 seconds after whatever it was that initiated the expansion. A number so small that it resists intuitive comprehension. A decimal point followed by 42 zeros and then a 1. A duration so brief that light itself, traveling at 300 million meters per second, would cross only the tiniest conceivable distance. The Planck length, which is to an atom what an atom is to approximately the entire observable universe. And at this moment, or rather just after this moment, for the moment itself remains hidden from us, the physics that we know and can describe begins to operate. The laws that govern particles and forces and the relationships between them start to apply, and the universe, whatever it was before, becomes something we can at least attempt to discuss with the language of science. What existed before the Planck time, or whether the word before has any meaning at that juncture, remains unclear, and we need not trouble ourselves with it now, for there is enough to consider in what came after, and it is enough to know that at 10 to the negative 43 seconds, something like a stage was set, even if the nature of that stage was nothing at all like the space we move through today, being unimaginably hot and dense and energetic, a seething quantum foam in which the very concepts of space and time had not yet settled into their familiar forms. And from this foam, or perhaps within this foam, the story that leads to your existence began. By the time the universe had reached an age of approximately 10 to the power of negative 32 seconds, still far less than a blink of an eye, still far shorter than any duration you could ever perceive or imagine perceiving, something remarkable had occurred. Though remarkable is perhaps not the right word for a narration meant to soothe you towards sleep. So let us say instead that something consequential had occurred, something that would determine the character of the cosmos for all of its subsequent history. And this was the period of inflation, a brief episode of exponential expansion during which the universe grew from something smaller than a proton to something perhaps the size of a grapefruit, or perhaps much larger, in a tiny fraction of a second, doubling and doubling and doubling again with each passage of an inconceivably small interval of time. This idea of inflation was developed by Alan Guth, a physicist working at Stanford in 1980. Who was trying to solve certain puzzles about the uniformity and flatness of the universe as we observe it, and his proposal, refined and elaborated by others in the years that followed, suggested that this brief period of accelerated expansion could explain why the cosmos appears so remarkably similar in every direction we look, and why its geometry appears so precisely balanced between different possible curvatures. And while the details of inflation remain a subject of active research, the general picture has become part of our standard account of cosmic history. One more piece of the story that leads from that first instant to this present moment. After inflation ended, the universe continued to expand and to cool, and as it cooled, the soup of energy and matter within it began to differentiate, to separate into distinct components, to allow particles to persist rather than being immediately annihilated or transformed. And during this time, at approximately 10 to the power of negative 6 seconds after the beginning, which is 1/1,000,000th of a second, still far too brief a time for any human experience but long enough for significant physics to have occurred. The universe existed in a state called a quark-gluon plasma, a kind of primordial broth in which the fundamental constituents of matter, the quarks and the gluons that bind them together, moved freely, not yet confined within the protons and neutrons that would later form, swimming through a space so hot and dense that the normal rules of confinement did not apply. This quark-gluon plasma remained theoretical for many decades, a prediction of our models of the early universe that could not be directly tested. But in the early years of this century, physicists at two great particle accelerator facilities managed to recreate, for the briefest of moments, conditions similar to those that prevailed in that first millionth of a second, and at the relativistic heavy ion collider at Brookhaven National Laboratory in New York, which produced its first relevant results around 2005, and at CERN's ALS detector in Geneva, which reported its findings around 2010. Gold and lead nuclei were smashed together at tremendous speeds, creating tiny fireballs of sufficient temperature and density to liberate quarks from their usual confinement, to produce, just for an instant, a droplet of the primordial plasma, confirming that our models of the early universe were at least plausible, that the conditions we imagine truly could produce the matter we observe. As the universe continued to cool, at perhaps 10 to the power of -5 seconds or thereabouts, the quarks began to condense, if that is the right word, to combine and to be confined, 3 at a time, into protons and neutrons, the particles that would eventually form the nuclei of atoms. And these protons and neutrons existed then in a sea of other particles, electrons and positrons and neutrinos and photons, all interacting vigorously, all in constant collision, the universe still hot enough and dense enough that light could not travel any significant distance without being absorbed or scattered. The cosmos opaque and glowing with an intensity beyond any star, and yet cooling, always cooling, as the expansion continued. And then, in the time between approximately 1 second and 3 minutes after the beginning, something happened that matters very much to the story we are telling, which is the story of why you are made of matter that should not exist. And this was the period of primordial nucleosynthesis, during which the first atomic nuclei were forged, not in the hearts of stars, for there were no stars yet, not in the explosions of supernovae, for there were no supernovae yet, but simply in the cooling plasma of the early universe itself. Protons and neutrons combining to form the nuclei of the lightest elements, a process that was essentially complete by the time 3 minutes had elapsed. The physicist George Gamow and his student Ralph Alpha had predicted this process in a paper published in 1948, working out the nuclear physics of the early universe and calculating what abundances of light elements should have been produced, and their predictions, refined over subsequent decades, match remarkably well with what we observe: approximately 75% hydrogen by mass, approximately 25% helium, and tiny trace amounts of lithium, and perhaps a breath of beryllium, and nothing heavier. For by the time 3 minutes had passed, the universe had cooled and thinned too much for further nuclear reactions to occur, and the heavier elements, the carbon in your cells, and the oxygen in your breath, and the iron in your blood, would have to wait for the first stars to form and to die, billions of years in the future, So by the end of those first 3 minutes, the universe had established its chemical inventory for the long ages to come. A vast cloud of hydrogen and helium expanding and cooling, still opaque with light, still too hot for atoms to form, for electrons to settle into orbit around nuclei. And this condition persisted for a remarkably long time by human standards, though a mere moment by cosmic ones. Approximately 380,000 years of gradual cooling and expansion. The universe slowly becoming more diffuse. The collisions between particles becoming less frequent. The temperature dropping from billions of degrees toward mere thousands. And then, at around that 380,000-year mark, the universe cooled enough for electrons to combine with nuclei to form the first true atoms, hydrogen and helium atoms settling into stability. And as this happened, something remarkable occurred, which was that the universe became transparent for the first time. The photons that had been trapped for all those hundreds of thousands of years suddenly free to travel, streaming outward in all directions, and we can still detect those photons today, stretched and cooled by the expansion of the universe over the subsequent 13.8 billion years, now appearing not as visible light, but as faint microwaves coming from every direction in the sky. And this is what we call the cosmic microwave background radiation. This radiation was first detected in 1965 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Laboratories in New Jersey, using an instrument called the Holmdel horn antenna, a large horn-shaped radio receiver that had originally been built to detect signals bounced off early communications satellites. And Penzias and Wilson found, to their initial frustration, that no matter where they pointed their antenna, no matter what they did to eliminate possible sources of interference, there was always a faint hiss of microwave radiation coming from all directions equally, a signal that had no apparent source, that could not be attributed to any known object or phenomenon. And after much investigation, and after consulting with theoretical physicists at nearby Princeton who had been predicting exactly such a signal, they concluded that they had detected the cooled remnant of the radiation from the early universe, the afterglow of the hot, dense state that had existed hundreds of thousands of years after the Big Bang. This cosmic microwave background is sometimes called the baby picture of the universe, an image of the cosmos as it was just 380,000 years old, still very young by astronomical standards. And while this image is far too late to show us the first 3 minutes directly, it confirms the general picture we have developed. It shows us a universe that was remarkably uniform, but not perfectly so. Slightly hotter in some places and slightly cooler in others. Tiny fluctuations that would eventually grow, over billions of years of gravitational attraction, into the galaxies and clusters and superclusters we observe today. The cosmic web of matter in which our own Milky Way is one small node among billions, and so we have traced, as gently as we can, the story of the first 3 minutes and a little beyond, from the Planck, time to inflation, to the quark-gluon plasma, to the formation of protons and neutrons, to the synthesis of hydrogen and helium and lithium, the basic ingredients from which everything else would be made. And then onward to that moment, 380,000 years later, when the universe first became transparent and left us a message we could still read billions of years later. sitting here on a small planet orbiting an ordinary star, made of atoms that have been cycling through stars and space and planets for generation after generation. Since the beginning of it all, in those first minutes that Steven Weinberg described so patiently, and that we have now walked through ourselves, slowly, as if through a garden, noticing each transformation, each quiet step in the long story that leads from then to now, from nothing to everything, from the cosmic fireball to you, lying here, listening, perhaps beginning to feel the pleasant heaviness of approaching sleep. Let us turn now to one of the quieter mysteries of physics, a puzzle that sits at the very foundation of your existence, and yet one that asks nothing of you except perhaps a moment of gentle contemplation before you rest. This is the story of antimatter, which sounds rather more dramatic than it needs to be, and of a mirror that physics held up to the universe only to find that the reflection did not quite match what we expected. And in that small discrepancy lies the reason you are here at all. In the year 1928, a young English physicist named Paul Dirac was working at Cambridge on a problem that had troubled the brightest minds of his generation. He was trying to reconcile two great theories that had emerged in the early 20th century: quantum mechanics on one hand and Einstein's special relativity on the other, and the mathematics required to unite them was formidable indeed. Dirac was 25 years old, quiet and precise in his manner, the sort of person who would sit in complete silence at dinner parties because he could not see the point of speaking unless he had something specific to communicate. He approached physics with this same economy, looking for the simplest possible formulation of the deepest possible truths. What emerged from his calculations was an equation of such startling elegance that physicists have called it the most beautiful equation in all of physics, though Dirac himself would probably have been uncomfortable with such praise. The equation described the behavior of electrons in a way that was consistent with both quantum mechanics and special relativity, and it did so with a mathematical grace that suggested Dirac had not invented something but rather discovered it, as one might discover a seashell on a beach that had been waiting there all along. The equation fit on a single line, and it explained with perfect precision how electrons spin and how they interact with electromagnetic fields. And it made predictions that experiments would later confirm with extraordinary accuracy. But there was something unexpected in the equation, something Dirac did not anticipate when he first wrote it down. The mathematics seemed to demand the existence of a particle that no one had ever seen, a kind of mirror image of the electron. This particle would have the same mass as an electron, exactly the same in every way, but it would carry a positive electrical charge instead of a negative one. Dirac was initially uncertain what to make of this, as scientists often are when their equations tell them something they were not looking for. He considered various interpretations, including the possibility that this mysterious positive particle might somehow be the proton, though the proton was nearly 2,000 times heavier than the electron, and this seemed unlikely. Eventually, Dirac came to accept what his mathematics was telling him, that there should exist in nature a kind of anti-electron, a particle of positive charge that was the electron's exact opposite in that one essential property. The physics community received this prediction with a mixture of fascination and skepticism, which is a healthy response to any extraordinary claim. But the wait for confirmation was not long. In 1932, a young American physicist named Carl Anderson was working at the California Institute of Technology, which is often called Caltech, studying cosmic rays with an instrument called a cloud chamber. A cloud chamber is a beautifully simple device. In essence, a sealed container filled with supersaturated vapor. And when charged particles pass through this vapor, they leave trails of tiny droplets behind them, much as an aircraft leaves a contrail across the sky. By placing the chamber in a magnetic field, Anderson could observe how these trails curved. Because charged particles bend in magnetic fields in ways that reveal their properties. A negatively charged particle curves one way, a positively charged particle curves the other, and the tightness of the curve tells you about the particle's mass and speed. Anderson was photographing these trails systematically, patient work that involved taking many hundreds of photographs and studying each one carefully for anything unusual. And on the 2nd of August, 1932, he captured an image that would change our understanding of the universe. The photograph showed a particle trail that curved the wrong way for an electron, indicating a positive charge. And yet, the curve was too tight to be a proton, indicating a mass much smaller than a proton's mass. The only explanation that fit the evidence was that Anderson had photographed exactly the particle Dirac had predicted, an anti-electron with positive charge and electron mass. Anderson called it the positron, a name that has stuck ever since. And for this discovery, he was awarded the Nobel Prize in Physics in 1936, sharing it with Victor Hess, who had discovered cosmic rays themselves. The existence of the positron confirmed something profound about the architecture of reality. For every particle of matter, there exists a corresponding particle of antimatter, identical in mass, but opposite in charge. The electron has its positron. The proton has its antiproton. Even the neutron, which carries no charge, has an antineutron that differs from it in subtler ways related to the arrangement of the quarks within. This symmetry runs through the entire particle zoo, every creature matched with its mirror twin. And when matter meets antimatter, something remarkable happens. If an electron encounters a positron, the two particles do not bounce off each other, nor do they pass through one another unaffected. Instead, they annihilate completely, converting all of their mass into pure energy in the form of gamma rays. This is the equation E equals mc squared, made manifest in the most direct way imaginable. The mass of the electron and the positron, which is not very much mass at all, transforms entirely into electromagnetic radiation. Each particle produces a gamma-ray photon with an energy of 511,000 electron volts, or 511 keV as physicists write it. And these two photons fly off in opposite directions, conserving the momentum that the original particles possessed. Nothing of the electron and positron remains except light. This process works the other way as well. Under the right conditions, a sufficiently energetic photon can spontaneously transform into an electron and a positron, creating matter and antimatter from pure energy. This happens routinely in particle physics laboratories and in the violent environments of the cosmos, near black holes and in the hearts of supernovae. The universe is constantly transforming energy into matter-antimatter pairs and matter-antimatter pairs back into energy. A quiet commerce that proceeds according to rules first glimpsed in Dirac's beautiful equation. In the decades since Anderson's discovery, physicists have learned to create and manipulate antimatter with increasing sophistication. At CERN, the European Organization for Nuclear Research near Geneva, scientists have built machines capable of producing antiprotons and combining them with positrons to create complete atoms of antihydrogen. An antihydrogen atom is the antimatter equivalent of ordinary hydrogen, with a positron orbiting an antiproton in the same way that an electron orbits a proton in regular hydrogen. Creating such atoms is extraordinarily difficult because antimatter annihilates instantly upon contact with ordinary matter. And everything in our world, including the walls of any container you might try to put antimatter in, is made of ordinary matter. The first successful creation of antihydrogen atoms was achieved by the Athena experiment at CERN in 2002. These atoms existed for only the briefest moments before they touched the walls of the apparatus and vanished in tiny flashes of annihilation. But the achievement demonstrated that antihydrogen was real, that complete atoms of antimatter could be assembled from their component parts. Later experiments refined the technique considerably. The Alpha collaboration, also at CERN, developed methods to trap antihydrogen atoms using magnetic fields, holding them suspended in vacuum away from the material walls that would destroy them. By 2011, Alpha could keep antihydrogen atoms trapped for over 1,000 seconds, more than 16 minutes, long enough to begin careful studies of their properties. These studies aim to answer a question of profound importance: whether antimatter behaves exactly like matter in every way, or whether there are subtle differences that might explain one of the deepest mysteries in physics. You see, the symmetry between matter and antimatter creates a terrible puzzle when we think about the origin of the universe. In the first moments after the Big Bang, when the universe was unimaginably hot and dense, energy was constantly converting into matter and antimatter according to the rules we have discussed. Photons became electron-positron pairs. More energetic processes created quarks and antiquarks, which combined into protons and antiprotons, neutrons and antineutrons. The early universe was a seething foam of particles and antiparticles, appearing from energy and annihilating back into energy, over and over again at a rate difficult to comprehend. As the universe expanded and cooled, this process slowed and eventually stopped. The energy density dropped below the threshold needed to create new particle pairs. And so whatever particles remained at that point, whatever matter and antimatter had not yet found partners to annihilate with, would be the matter and antimatter that the universe would contain forever after. Here is where the mystery becomes apparent, and it is a mystery that touches you personally, though it asks nothing of you at this late hour. If the universe began in a state of perfect symmetry, and if the laws of physics treat matter and antimatter with perfect equality, then the Big Bang should have produced exactly equal amounts of matter and antimatter. Exactly equal. Not almost equal. Not very nearly equal. But precisely and perfectly equal. One particle of antimatter for every particle of matter. matched in a cosmic balance of perfect parity. And if exactly equal amounts were produced, then, as the universe cooled and the particles sought each other out, every particle of matter would have found a particle of antimatter to annihilate with. Every electron would have met a positron. Every proton would have encountered an antiproton. The annihilation would have been complete and universal, converting all the mass that had briefly flickered into existence back into pure radiation. The universe would contain no atoms, no molecules, no planets, no stars. It would be a vast, cold sea of photons, the fading glow of that primordial annihilation, empty of structure, empty of complexity, empty of the possibility of life. You would not exist. I would not be speaking these words. There would be no one to wonder at the strangeness of physics and no physics to wonder at. The cosmos would be a diffuse and featureless wash of electromagnetic radiation, cooling slowly as the universe expanded, thinning out across the eons into something approaching absolute emptiness. This is not a dramatic statement meant to unsettle you as you rest, but simply a calm description of what physics, in its perfect symmetry, would predict. Yet here you are, made of protons and neutrons and electrons, lying somewhere on a planet made of the same, orbiting a star made of the same, in a galaxy surrounded by billions of other galaxies, all composed of matter, ordinary matter, and very little antimatter to be found anywhere. The universe is manifestly not a diffuse glow of annihilation photons. It is rich with structure, complex beyond measure, and you are part of that complexity. Something about our understanding of the symmetry between matter and antimatter must be incomplete. The mirror that should have shattered everything, that should have cancelled matter and antimatter into a silent sea of light, somehow allowed a tiny residue of matter to survive. The imbalance required is surprisingly small. For every billion particles of antimatter in the early universe, there must have been approximately 1,000,000,001 particles of matter. Just one extra particle of matter for every billion pairs. That tiny excess, that almost imperceptible weight on one side of the cosmic scale, was enough. The billion pairs annihilated, converting their mass into the radiation that we now detect as the cosmic microwave background, that faint afterglow of the Big Bang that fills the sky in every direction. But the one extra particle in each billion had no partner to annihilate with, and so it survived. Those survivors, that 1 in a billion residue of matter, became everything we see around us. Every atom in your body, every star in the sky. Why there was an imbalance at all remains one of the great unsolved problems in physics. The symmetry that Dirac's equation revealed seems so perfect, so beautiful, so complete. Yet the universe does not obey it with perfect precision. Somewhere in the laws of physics, there must be a subtle asymmetry, a small preference for matter over antimatter, and physicists call this hypothetical asymmetry by the name of the Soviet physicist who first analyzed the conditions necessary for it to exist, Andrei Sakharov. We know that such an asymmetry must exist, because we exist, but we have not yet identified its source with certainty. For now, let that mystery rest unresolved, as so many mysteries in physics must rest. The equations of Dirac still stand as monuments of beauty and insight, The positron still annihilates with the electron into two photons of precisely 511 keV. The antihydrogen atoms at CERN still hover in their magnetic traps, waiting to be questioned about the secrets they might hold. And you are still here, made of matter that should not exist, proof that the universe is stranger and more generous than its perfect symmetries would suggest, drifting now, perhaps, toward sleep. And so we come now to consider the numbers themselves, the actual accounting of what happened in those earliest moments, and I should tell you that the numbers are quite remarkable in their smallness, in the delicacy of the imbalance that allowed everything you know to exist. When we speak of the asymmetry between matter and antimatter, we are not speaking of some dramatic preponderance, not some overwhelming victory of one form over the other, but rather of something so subtle, so nearly imperceptible, that it almost seems like a rounding error in the arithmetic of creation. For every billion particles of antimatter that emerged from the cooling universe, there were 1,000,000,001 particles of matter. That is all. One extra grain for every billion pairs. One slight tipping of the scales that would have been invisible to any observer. Had any observer been possible in that furnace of creation? The asymmetry, when we express it in the language of physics, amounts to roughly 1 part in 10 to the 9th power, which is to say 1 part in a billion, and this number is so small that you might wonder how we could ever hope to measure it, how we could ever peer back through nearly 14 billion years of cosmic history and count the imbalance that occurred in the first fraction of a second. But the universe, in its patient way, has preserved evidence of this accounting, has written the record in light that has traveled to us from the most distant epoch we can observe. The light of the cosmic microwave background radiation that fills all of space with its faint and ancient glow. This light, this whisper of the early universe, carries within it information about the relative abundance of ordinary matter compared to the sea of photons that emerged from that primordial fire. And by measuring this ratio with extraordinary precision, we can work backward to understand what must have happened when matter and antimatter were being created and destroyed in that earliest furnace. The measurement of this ratio has been refined over decades through a series of satellite missions designed to map the cosmic microwave background with ever-increasing precision. And I shall tell you about 2 of these missions now, for they represent some of humanity's most careful attempts to understand the conditions of the early universe. The first of these was called the Wilkinson Microwave Anisotropy Probe, often shortened to WMAP, which was launched by NASA in the year 2001 and operated until 2010, spending those years at a special point in space called the second Lagrange point, about 1.5 million kilometers from Earth, where it could observe the entire sky without interference from our planet's own warmth. WMAP measured tiny fluctuations in the temperature of the cosmic microwave background, variations so small that they amount to differences of only a few millionths of a degree. And from these measurements, combined with other observations, unsure, scientists were able to determine the density of ordinary matter in the universe with unprecedented accuracy. Following WMAP came an even more precise instrument, the Planck satellite, launched by the European Space Agency in 2009, which carried detectors cooled to temperatures barely above absolute zero. allowing them to sense the cosmic microwave background with sensitivity that exceeded all previous measurements. Planck operated until 2013, and the data it returned has been analyzed for years afterward, refining our understanding of the universe's contents and history. From both of these missions, and from the careful work of hundreds of scientists who analyzed their observations, we have arrived at a number that expresses the ratio of baryons to photons in our universe, where baryons is the term physicists use for particles made of quarks, which includes protons and neutrons, the constituents of ordinary matter. This ratio, as measured through the cosmic microwave background, is approximately 6 × 10 to the negative 10th power, which can also be written as 0.000000000066, or roughly 6 baryons for every 10 billion photons that fill the universe. This number, so small and so precise, is a fossil of the asymmetry that occurred in the first moments of cosmic history. Each of those baryons, each of those protons and neutrons that would eventually form the nuclei of atoms, represents one of the survivors, one of the particles of matter that remained after the Great Annihilation, when all the antimatter had found its partner and converted to light. The photons themselves, the cosmic microwave background radiation, are in part the product of that annihilation, the remains of the energy released when matter and antimatter met and destroyed each other. So the ratio of baryons to photons is telling us, in its quiet numerical way, how many particles survived compared to how many were destroyed. And from this we can calculate that the original asymmetry was indeed roughly 1 part in a billion. 1 extra matter particle for every billion pairs that were created and annihilated. The question of why this asymmetry should exist, why the universe did not produce exactly equal amounts of matter and antimatter, and therefore annihilate completely into a sea of radiation containing nothing that could form stars or planets or living beings, was addressed in a remarkable paper published in 1967 by a Soviet physicist named Andrei Dmitrievich Sakharov. The circumstances of Sakharov's life and work are themselves worth considering, for they remind us that the people who study the most abstract questions of physics are themselves embedded in the complexities of human history, with all its conflicts and compromises. Sakharov had spent years working on the development of thermonuclear weapons for the Soviet Union, playing a central role in the creation of the hydrogen bomb. And it was during this period, while contemplating the most destructive applications of nuclear physics, that he also turned his mind to the most fundamental questions of cosmology, to the puzzle of why the universe contains matter at all. In his 1967 paper, Sakharov outlined 3 conditions that would be necessary for the universe to develop an asymmetry between matter and antimatter. 3 requirements that any physical process would need to satisfy in order to generate more baryons than antibaryons from an initially symmetric state. These 3 conditions have come to be known as the Sakharov conditions, and they remain the framework within which physicists attempt to understand baryogenesis, the creation of the matter asymmetry, to this day. The first condition is that there must exist some process that violates the conservation of baryon number, which means a process that can change the total number of baryons in the universe, creating or destroying them rather than merely rearranging them. Without such a process, If baryon number were absolutely conserved, then the universe could never develop an imbalance. For whatever amount of matter and antimatter existed at the beginning would persist unchanged forever. The second of Sakharov's conditions requires that the laws of physics must violate certain symmetries known as C and CP, where C stands for charge conjugation, which is the operation of swapping particles with their antiparticles, and P stands for parity, which is the operation of viewing the universe as if in a mirror. If the laws of physics were perfectly symmetric under both of these operations, then any process that created an excess of matter would be exactly balanced by a corresponding process, creating an excess of antimatter, and no net asymmetry could develop. The violation of these symmetries, particularly the combined symmetry of CP, is therefore essential, for it allows the universe to prefer matter over antimatter in at least some of its interactions, creating a slight bias that can accumulate over time. The third condition that Sakharov identified is that these processes must occur away from thermal equilibrium, which is to say, they must happen in a universe that is changing, expanding, cooling, rather than in a static state where all processes have reached a balance with their reverse processes. In thermal equilibrium, any process that creates matter would be exactly balanced by the reverse process that destroys matter. And again, no net asymmetry could accumulate. But the early universe was far from equilibrium, expanding and cooling rapidly. And this departure from equilibrium allowed processes to occur that could not be undone, allowed the asymmetry to be frozen in rather than washed away. Sakharov's life took a remarkable turn in the years following this paper, as he became increasingly concerned with the moral implications of nuclear weapons and the treatment of human rights in the Soviet Union. He became an advocate for disarmament and for political freedom, activities that brought him into conflict with the Soviet government and eventually led to his internal exile to the city of Gorky, where he was held from 1980 until 1986. He was awarded the Nobel Peace Prize in 1975, though the Soviet authorities did not permit him to travel to receive it, and his wife, Elena Bonner, accepted it on his behalf. That the same mind that conceived the conditions for the existence of matter in the universe also worked for the reduction of nuclear arsenals and the protection of human dignity is one of those conjunctions that reminds us how the pursuit of knowledge and the pursuit of justice can sometimes flow from the same source, from the same impulse to understand the universe and our responsibilities within it. Returning now to the question of the cosmic asymmetry, we might wonder whether the imbalance we observe in our part of the universe is truly universal, whether perhaps somewhere in the distant cosmos there are regions where antimatter dominates, where antiprotons and positrons have formed anti-atoms and anti-planets. If such regions existed, then the matter asymmetry might be only a local phenomenon, with the universe as a whole containing equal amounts of matter and antimatter, separated into distinct domains that do not touch and therefore do not annihilate. This possibility, while not ruled out by pure logic, faces severe observational constraints. For if such antimatter domains existed anywhere in the observable universe, we would expect to see evidence of annihilation at their boundaries. Gamma rays produced where matter and antimatter meet and destroy each other. No such signal has been observed, suggesting that if antimatter domains exist at all, They must be extremely rare or extremely far away. To search for direct evidence of cosmic antimatter, scientists have deployed an instrument of remarkable ambition on the International Space Station, a particle physics detector called the Alpha Magnetic Spectrometer, or AMS-022, which has been operating since 2011. This experiment, led by the physicist Samuel Chao-Chung-Ting, who shared the Nobel Prize in Physics in 1976 for the discovery of a particle called the J-Pizi meson, uses a large magnet to bend the paths of cosmic ray particles, allowing it to distinguish between matter and antimatter by the direction of their curvature. If antimatter atoms, particularly antihelium nuclei, were arriving at Earth from distant regions of space, AMS-02 would be able to detect them, providing evidence that pockets of antimatter exist somewhere in the cosmos. In the years since its installation on the space station, AMS-02 has recorded billions of cosmic ray particles, building up statistics with extraordinary patience. Measuring the composition of the high-energy particles that rain upon us from throughout the galaxy and beyond, it has detected antiprotons and positrons, but these are known to be produced in collisions between ordinary cosmic rays and interstellar gas. Secondary particles created in energetic processes rather than primordial antimatter surviving from the early universe. What it has not found, despite years of searching, is any convincing evidence of heavier antimatter nuclei, such as antihelium or anticarbon, the kind of particles that would be produced if antimatter stars and antimatter planets existed somewhere in the cosmos, sending their debris across the light years to reach our detectors. The absence of cosmic antimatter in the observations of AMS-0202, combined with the lack of gamma-ray signals from matter-antimatter boundaries, confirms what the cosmic microwave background suggested, that the asymmetry between matter and antimatter is a property of the entire observable universe, not merely our local neighborhood. From the most ancient light we can observe to the highest energy particles arriving at the space station, the evidence consistently points to a cosmos made entirely of matter, with antimatter present only in the tiny amounts produced by energetic collisions or appearing briefly in laboratory experiments before annihilating with its surroundings. And so we arrive at the picture that emerges from decades of observation and theory. A picture of a universe that began in a state of apparent symmetry but developed, through processes we are still working to fully understand, a slight preference for matter over antimatter, an imbalance of 1 part in a billion that would prove to be sufficient for everything that followed. That extra particle in every billion, that one lonely survivor for every billion pairs that annihilated into light, would become the raw material for all the complexity and structure we see around us, for galaxies and stars and planets, and the subtle arrangements of atoms that make up living things. The numbers are quiet, undramatic, almost disappearing into the noise of cosmic bookkeeping. Yet they are the reason anything exists at all, the margin by which existence overcame oblivion. And so we come now to one of the quieter revelations in the history of physics, a discovery that arrived not with fanfare, but with careful measurement, with patient observation of particles doing something they were not, according to the prevailing understanding of the time, supposed to do. This is the story of what physicists call CP violation, which is perhaps not the most poetic name for a phenomenon, but which describes something rather profound about the universe in which you find yourself existing. It describes a subtle preference, a gentle favoritism built into the very fabric of reality, one that may have played some role in allowing matter to persist, in allowing atoms to form, in allowing you to be here now, breathing softly, perhaps growing drowsy, as we consider together how the cosmos chose, ever so slightly, to favor one kind of thing over another. To understand what CP violation means, we must first understand what physicists expected to be true. For many decades, there was a comfortable assumption that the laws of physics possessed certain symmetries, certain ways in which they remained unchanged when you performed particular transformations. One of these symmetries was called charge conjugation, which is the operation of replacing every particle with its antiparticle. An electron becomes a positron, a proton becomes an antiproton, and so forth. The laws of physics, it was thought, should look exactly the same after this swap. Another symmetry was called parity, which is essentially the operation of looking at the universe in a mirror, of flipping left and right. And for a long time, physicists believed that if you combined these two operations, if you both swapped all particles for antiparticles and also reflected everything in a mirror, the laws of physics would remain perfectly unchanged. This combined operation was called CP symmetry, and it seemed like a reasonable thing to believe, a kind of deep even-handedness built into nature. But nature, it turns out, is not quite so even-handed, and this was discovered in 1964 at a place called Brookhaven National Laboratory, which sits on Long Island in New York State, in a landscape of pine barrens and quiet roads, not far from the Atlantic Ocean. Two physicists, James Cronin and Val Fitch, were there conducting an experiment that was, in many ways, quite straightforward, though it required considerable patience and precision. They were studying particles called neutral kaons, which are mesons, composite particles made of a quark and an antiquark bound together. The neutral kaon is a particularly interesting particle because it exists in a kind of quantum superposition of two different states, which physicists label K-long and K-short, reflecting the fact that one of these states lives longer than the other before decaying into different particles. The experiment that Cronin and Fitch designed involved sending a beam of neutral kaons down a long pathway, a beamline stretching 57 feet through the experimental apparatus. This may not sound terribly impressive in an age of particle accelerators that span many kilometers, but at the time it was a carefully constructed corridor designed to allow the kaons sufficient time to reveal their nature. The K-short particles, true to their name, would decay quickly, typically into two pions, which are lighter mesons. The K-long particles, by contrast, were expected to decay only into 3 pions, never into 2, because CP symmetry demanded it be so. The mathematics of the situation, if CP symmetry held exactly, required that the K-long state could not produce a 2-pion final state. And so the experiment proceeded, with detectors positioned to observe what emerged from the far end of the beamline, where only the K-long particles should have survived, the K-short ones having already decayed away much earlier in their journey. What the detectors were looking for, really, was an absence. They expected to see only 3 pion decays from the K-long kaons, and the 2 pion decays should have been essentially non-existent. But that is not what they found. Instead, a tiny fraction of the K-long particles, roughly 2 out of every 1,000, were decaying into 2 pions rather than 3. It was a small effect, a subtle deviation, but it was unmistakably there, and it meant that CP symmetry was not exact. The universe, in this quiet corner of particle physics, was showing a preference. It was treating matter and antimatter, when combined with mirror reflection, just slightly differently. This discovery was significant enough that Cronin and Fitch were awarded the Nobel Prize in Physics in 1980, 16 years after their original observation. The delay is not unusual in physics, where revolutionary findings often require time to be digested, verified, and understood within a broader theoretical framework. And in this case, the theoretical understanding would come from 2 Japanese physicists named Makoto Kobayashi and Toshihide Masukawa, who in 1973 proposed an explanation for how CP violation could arise within the framework of what we now call the Standard Model of Particle Physics. Their insight was that if there were at least 3 generations of quarks, 3 pairs of these fundamental particles rather than 2, then the mathematics would naturally allow for CP violating effects to appear. At the time of their prediction, only 3 quarks were known to exist: the up, down, and strange quarks, but their theory required 6. The subsequent discoveries of the charm quark, the bottom quark, and finally the top quark vindicated their framework, and Kobayashi and Masukawa received the Nobel Prize in 2008 for this theoretical work. The mechanism they proposed is encoded in something called the Kabibbo-Kobayashi-Masukawa matrix, which is a mathematical object describing how quarks of different types mix and transform into one another through the weak nuclear force. This matrix contains within it a special number called a complex phase, and it is this phase that permits CP violation to occur. It is a remarkably subtle thing, a single parameter buried in the equations, and yet it has consequences that ripple out to the largest scales of cosmology. In the years following the original kaon experiments, physicists sought to study CP violation in other systems, to measure it more precisely and to test whether the Kobayashi-Masukawa framework could account for everything observed. 2 major experiments were constructed for this purpose. One was called BABA, and it operated at the Stanford Linear Accelerator Center in California from 1999 to 2008. The other was called BELL, and it ran at the KEK laboratory in Japan over a similar period. Both experiments were designed to produce enormous numbers of B mesons, which are particles containing a bottom quark, and to study the decays of these particles with exquisite precision. The B meson system was known to be a promising place to look for CP violation because the theoretical predictions suggested the effects should be larger there than in kaons, and therefore easier to measure. And indeed, both experiments observed CP violation in B meson decays, confirming the predictions of the Kobayashi-Masukawa theory with remarkable accuracy. The complex phase in the mixing matrix was measured, and it matched what the standard model predicted. This was a triumph for theoretical physics, a vindication of a bold prediction made decades earlier. But there was also something troubling in these results, something that becomes apparent only when you consider the cosmological implications. You see, the amount of CP violation that has been measured in these experiments, and in all experiments conducted since, is far too small to explain why the universe contains any matter at all. When physicists calculate how much asymmetry between matter and antimatter the observed CP violation could have produced in the early universe, they find that it accounts for roughly 1 part in a billion of what would have been needed. The measured effects are real. They are present. They do represent a genuine preference of nature for matter over antimatter in certain processes, but the magnitude is vastly insufficient. It is as if you discovered that a gentle breeze could indeed push a boulder, but calculated that the breeze in question could move the boulder only 1 nanometer over the entire age of the universe, when what you needed to explain was how the boulder came to rest on the other side of a mountain. This discrepancy remains one of the great unsolved problems in physics. The Standard Model, for all its successes, cannot explain why you exist. It can demonstrate that nature does possess a small preference for matter, but that preference is not nearly strong enough to account for the matter-dominated universe we observe. There must be additional sources of CP violation beyond what we have discovered, hidden processes involving particles we have not yet detected, or mechanisms operating in ways we do not yet understand. The search continues, and in recent years, new discoveries have added to our catalogue of CP violating systems without yet solving the fundamental puzzle. In 2019, the LHCb experiment at CERN and CERN, which is part of the Large Hadron Collider complex in Switzerland, announced the discovery of CP violation in the decays of d mesons. These are particles containing charm quarks, and they represent a different corner of the particle physics landscape from the kaons and b mesons studied earlier. The observation was significant because it confirmed that CP violation is not confined to just 1 or 2 systems, but appears across multiple types of particles, as the Standard Model predicts. More recently, in 2025, the LHCb collaboration announced another milestone: the observation of CP violation in baryons. Baryons are particles made of 3 quarks, like the protons and neutrons that constitute your own body, and this was the first time CP violation had been definitively observed in such particles. Each new discovery adds to our confidence that we understand the basic mechanisms at work, but none of them have yet revealed the additional sources of asymmetry that the universe seems to require. The Standard Model's asymmetry, though real, remains vastly insufficient. And so we are left with a gentle mystery, one that does not demand immediate resolution, but simply invites quiet contemplation as you rest there, perhaps feeling your breath slow, perhaps noticing the weight of your body against whatever surface supports you. The universe, in its earliest moments, was a place of almost perfect balance, and yet some subtle influence tipped the scales, allowed a tiny excess of matter to survive. And from that excess arose everything you know. The stars, the planets, the oceans, the air, and you yourself, made of atoms that should not, by the simplest accounting, exist at all. The particles within you have descended from that ancient imbalance, have persisted through billions of years, have assembled themselves into the precise configuration that allows you to listen to these words and wonder at the strangeness of it all. The kaons in that 57-foot beamline at Brookhaven, decaying in ways that surprised the physicists watching, were revealing something true about the nature of existence. The universe is not perfectly symmetric. It has preferences, however slight, and though those preferences remain too small to fully explain your presence here, they point toward deeper truths waiting to be uncovered, waiting with infinite patience as the search continues in laboratories around the world, and as you continue, perhaps, to drift toward sleep. And so, when physicists gather at conferences or sit alone with paper and pencil in quiet offices, they do not despair at the mystery of our asymmetric universe, but rather they propose and refine and gently test their theories, each one a kind of whispered suggestion about what might have happened in those earliest moments. And it is these theories we shall now explore together, not as a catalogue of frustrations, but as a landscape of possibilities, each with its own elegance, its own predictions, and its own particular beauty that reveals how carefully humans can think about the cosmos, even when the cosmos has not yet revealed its secrets. One of the most influential and widely studied ideas emerged in 1986, when two physicists working in Japan, Masataka Fukujita and Tsutomu Yanagida, proposed a mechanism that has come to be known as leptogenesis. And this theory begins not with quarks and antiquarks directly, but rather with their lighter cousins, the leptons, which include electrons and neutrinos, those ghostly particles that pass through ordinary matter as though it were not there at all. And the idea is both simple in its outline and remarkably subtle in its details, suggesting that perhaps the asymmetry we observe today in matter over antimatter began first as an asymmetry in leptons over antileptons, which was then converted through the peculiar processes of the early universe into the asymmetry we see in protons and neutrons and all the atoms that comprise your body as it rests there, breathing gently, listening to these words. At the heart of leptogenesis lies a hypothetical particle called the right-handed neutrino. And here we must pause to explain what this curious name means. For in the quantum world, particles possess a property called handedness, which describes how their spin relates to their direction of motion, and the neutrinos we have detected in our experiments have always been left-handed, spinning in one particular orientation relative to their travel, while their antiparticles, the antineutrinos, have always been right-handed, and this perfect separation is itself a deep mystery. But the theory of leptogenesis proposes that there exist other neutrinos, very heavy ones never yet observed, which are right-handed, and these heavy right-handed neutrinos would have been created in abundance in the tremendous heat of the early universe. And when they decayed, when they broke apart into lighter particles, they did so in a way that ever so slightly favored the production of leptons over antileptons. This preference, this slight asymmetry in the decay of the heavy right-handed neutrinos, would have accumulated over the countless decays occurring throughout the early universe. And the theory proposes that the asymmetry thus generated was not permanent in its original form, but rather it was processed and transformed by other interactions, by the sphaleron processes we mentioned earlier, which, in that hot, dense era, could freely convert leptons into quarks and back again. And so the original asymmetry in leptons became distributed, became shared, became an asymmetry in both leptons and quarks together. And thus, the baryons, the protons and neutrons that would eventually form atoms, inherited their imbalance from the leptons, which had inherited it from the decays of particles so massive that they could only have existed in the very first moments after the Big Bang. The heavy right-handed neutrinos required by leptogenesis connect to another beautiful theoretical framework called the seesaw mechanism. And this mechanism was proposed to explain one of the enduring puzzles of particle physics, which is why ordinary neutrinos have any mass at all, and why that mass is so extraordinarily tiny, billions of times smaller than the mass of an electron, which is itself a very light particle. And the seesaw mechanism suggests that the reason ordinary neutrinos are so light is precisely because their right-handed counterparts are so heavy, with the two masses related like the ends of a seesaw, so that when one end goes up, the other goes down. And the heavier the right-handed neutrino, the lighter the ordinary neutrino becomes. And this elegant connection means that if leptogenesis is correct, then the very lightness of the neutrinos we detect today is a kind of fossil evidence, a trace of those heavy particles that once existed and whose asymmetric decays gave rise to the matter from which you are made. But leptogenesis is not the only theory that physicists whisper about when they contemplate the asymmetry of existence. And in 1985, a year before Fukujita and Yanagida proposed their mechanism, two physicists named Ian Affleck and Michael Dine suggested a different pathway, one that relies on a theoretical framework called supersymmetry, in which every known particle has a heavier partner, a kind of shadow particle that has not yet been detected, but which some physicists believe must exist to explain other mysteries of particle physics. And in the Affleck-Dine mechanism, the early universe contained fields, quantum fields spread throughout all of space. And these fields could take on particular configurations called flat directions, regions of field space where the energy did not change much as the field varied. And as the universe expanded and cooled, these fields could have developed asymmetries, imbalances between matter and antimatter, which were then transferred to ordinary particles as the fields decayed. And this mechanism has the advantage of being able to produce large asymmetries quite efficiently. And it has the disadvantage, shared with many theories involving supersymmetry, of relying on particles we have not yet found, though the search continues. Another category of theories focuses not on heavy new particles or supersymmetric fields, but rather on the electroweak force itself, one of the four fundamental forces of nature, which governs the behavior of particles at very high energies and which unified the electromagnetic force with the weak nuclear force in a great theoretical achievement of the 20th century. And these theories, collectively called electroweak baryogenesis, propose that the asymmetry of matter over antimatter was generated during a period when the universe cooled through a particular transition called the electroweak phase transition, when the Higgs field settled into its current state. And for this mechanism to work, this transition must have been of a special type, a first-order phase transition, which is like the way water can supercool below its freezing point and then suddenly crystallize, with bubbles of the new phase forming and expanding through the old phase. And at the boundaries of these bubbles, at the walls where the two phases meet, the conditions could have been just right for particles and antiparticles to behave differently, for the asymmetry to be generated and preserved. The challenge for electroweak baryogenesis is that in the standard model of particle physics, the model that describes all the particles and forces we have so far observed, the electroweak phase transition appears to be too smooth, too gentle, not sufficiently first order to produce the conditions necessary for generating the observed asymmetry, and so physicists search for new particles, new interactions that would modify the transition and make it more abrupt. And some of these searches are conducted at the Large Hadron Collider, that great ring of superconducting magnets buried beneath the Swiss-French countryside, where protons are accelerated to nearly the speed of light and smashed together in collisions that recreate, for the briefest of instants, conditions similar to those of the early universe. And while the collider has not yet found the new particles that would confirm electroweak baryogenesis, it has set limits on where those particles can hide, narrowing the possibilities, guiding the theorists toward more refined predictions. And then there are the more exotic theories, the ideas whispered at the edges of conferences, the speculations that delight theorists even as experimenters wonder how they might ever be tested. And among these is the idea of mirror matter, a concept that has been proposed and developed by various physicists over the decades, suggesting that for every particle we know, there exists a mirror partner, not just an antiparticle, but a truly separate particle that interacts with its own mirror forces, forming mirror atoms and mirror molecules, and perhaps even mirror stars and mirror planets, all invisible to us except through the force of gravity. And in some versions of this idea, the asymmetry we observe in our matter is balanced by an opposite asymmetry in mirror matter, so that the universe as a whole remains symmetric, with equal amounts of matter and antimatter. If one counts both the visible and mirror sectors together, there is also an approach called Dirac leptogenesis, which provides yet another variation on the theme, connecting the asymmetry of the universe to different properties of neutrinos. And this theory suggests that the asymmetry could have been generated through processes involving neutrinos with a particular type of mass, called a Dirac mass, rather than the Majorana mass assumed in standard leptogenesis. And the difference between these two types of mass relates to whether neutrinos are their own antiparticles, a question that experiments are still trying to answer. And so the search for the origin of matter asymmetry connects to fundamental questions about the nature of the neutrino, that most elusive and peculiar of particles. Speaking of neutrinos, we should note that our understanding of these particles took a tremendous leap forward in 1998, when an experiment called Super Kamiokande, a vast underground detector in Japan consisting of 50,000 tons of ultra-pure water surrounded by 11,000 sensitive light detectors, announced that it had observed neutrinos changing from one type to another as they traveled through the Earth. And this phenomenon, called neutrino oscillation, could only occur if neutrinos possess mass. A discovery that was surprising because the original standard model of particle physics had assumed neutrinos were massless. And this finding was so important that it led to the 2002 Nobel Prize in Physics being awarded to Raymond Davis Jr. and Masatoshi Koshiba, recognizing their pioneering contributions to the detection of neutrinos from astrophysical sources. And the fact that neutrinos have mass opens the door to leptogenesis and to other theories that require massive neutrinos. And it demonstrates that our understanding of the fundamental particles is still incomplete, still capable of surprising us. The discovery of neutrino mass led to a new generation of experiments designed to study these ghostly particles in ever greater detail. And among the most ambitious is the Deep Underground Neutrino Experiment, known by its acronym DUNE, which is currently under construction in the Sanford Underground Research Facility in South Dakota, a facility housed in what was once the Homestake Gold Mine, nearly a mile beneath the surface of the Black Hills. And this experiment will send a beam of neutrinos from Fermilab in Illinois, traveling 800 miles through the Earth's crust, to be detected by enormous tanks of liquid argon waiting in the depths of the mine. And one of the primary goals of DUNE is to search for CP violation in neutrino oscillations, to determine whether neutrinos and antineutrinos behave differently as they transform from one type to another. And if such CP violation is found, it would provide a crucial piece of evidence for leptogenesis, suggesting that the asymmetric decays of heavy right-handed neutrinos in the early universe could indeed have favored matter over antimatter. The DUNE experiment is expected to begin taking data by the late 2020s, and physicists around the world are preparing for what it might reveal, knowing that the results could transform our understanding of why the universe contains matter, why you exist at all. Though, of course, the experiment might also produce results that are unexpected, that confound current theories and send theorists back to their notebooks to dream up new explanations. And this, too, would be valuable, for science advances not only when theories are confirmed, but also when they are found wanting and must be replaced. And so the theories accumulate: leptogenesis and Affleck-Dine and electroweak baryogenesis and mirror matter and Dirac leptogenesis and others still. Each one a careful proposal, each one consistent with what we know, each one making predictions that might someday be tested. And the theorists who dream these possibilities do so not in frustration, but in wonder, marveling that the universe is subtle enough to hide its secrets so well, and patient enough to wait for us to find them. And the experiments continue, deep underground and at great colliders, and in the quiet analysis of data, all of them searching for the answer to a question that is, in the end, the most personal question of all, which is simply why you are here, breathing, listening, existing in a cosmos that had every reason to be empty. Let us turn now to something quite close to you, something so near that it could not possibly be any nearer, because it is you. It is the very substance of which you are composed, the atoms that at this very moment are arranged in the particular pattern that makes you who you are, lying there in the quiet dark, breathing slowly, listening to these words, being gently carried towards sleep by the simple fact that you exist at all, which is itself a mystery written into every particle of your being. Consider, if you will, and there is no urgency in this consideration, the breath you just took, the one before this one, the gentle expansion of your lungs as air flowed in through your nose or mouth and filled those delicate branching passages. those tiny sacs where oxygen crosses into your blood, and think for a moment about that oxygen, about what it is, about where it came from, because the story of those atoms is very old indeed. Far older than you might casually suppose when you are simply breathing without thinking about it, which is most of the time, and rightly so. The oxygen in your lungs, the oxygen that is right now diffusing across the thin membranes of your alveoli and binding to the hemoglobin in your red blood cells, is composed almost entirely of a particular variety called oxygen-16, which makes up approximately 99.762% of all the oxygen you will ever breathe. And this oxygen-16 was not present at the beginning of the universe. It did not emerge from the first few minutes of existence when the cosmos was a hot, dense soup of particles and radiation. No, this oxygen was forged much later, in the cores of massive stars. Stars that lived their brief and brilliant lives and then exploded in supernovae that scattered their newly made elements across the void. And some of that scattered material eventually found its way into a collapsing cloud of gas and dust that became our solar system, and then our planet. And then, after a very long time of geological and biological processes that we need not detail just now, into you, into the breath you are taking at this very moment. So the oxygen keeping you alive as you lie there listening was cooked inside a star that died before our sun was born. And there is something rather peaceful about that, something that connects you to the deep past of the universe in a way that requires no effort on your part, no special knowledge or training. Because it is simply true. It is simply what you are made of, stellar ash arranged into a person who is getting sleepy. And speaking of what you are made of, let us consider the protons in your body. The protons that sit at the heart of every hydrogen atom, every oxygen atom, every carbon and nitrogen and calcium and phosphorus atom. All the protons in all the atoms that compose you. And let us think about how long they have been around, because protons are extremely stable particles. So stable, in fact, that physicists have spent considerable effort trying to determine exactly how stable they are. Deep beneath a mountain in Japan, in a place called the Kamioka Observatory, there is a detector called Super Kamiokande, which is essentially an enormous tank filled with 50,000 tons of ultra-pure water, surrounded by thousands of sensitive light detectors. And one of the things this detector is designed to do is watch for proton decay, to catch the rare event of a proton falling apart into other particles, which certain theories of physics predict should happen. Eventually, if you wait long enough. But despite decades of patient watching, no proton decay has ever been observed. And the experiments have established that if protons do decay at all, their average lifetime must be greater than 10 to the power of 34 years, which is a 1 followed by 34 zeros. A number so large that it is difficult to hold in the mind, far longer than the current age of the universe, which is a mere 13.8 billion years, a 1 followed by only 10 zeros. What this means, in practical terms, is that the protons in your body, the protons that were created in the first fraction of a second after the Big Bang, have been around for 13.8 billion years and show no sign of going anywhere. They are phenomenally, almost inconceivably stable. They have survived the entire history of the cosmos, the formation of the first stars, the explosion of those stars, the coalescence of new solar systems, the slow emergence of life on at least one small planet. And now here they are, arranged into you, into your bones and muscles and blood and brain, the same protons, having experienced all of that history, now quietly participating in the biochemistry of a person who is drifting towards sleep. And while we are speaking of particles that have been around since near the beginning, let us think about the hydrogen in your body, because hydrogen is the simplest element. Just one proton and one electron. And the hydrogen atoms in you are in some sense the most ancient atoms you contain, their protons dating back to the first seconds of cosmic history. And much of this hydrogen is bound up in water. In the water that makes up roughly 60% of your body mass. And this water has had quite a journey. The hydrogen atoms in the water in your body were present in the first 3 minutes after the Big Bang, when the universe was still hot enough for nuclear fusion to occur throughout all of space. And during those first 3 minutes, the protons that had formed combined with neutrons to make the first atomic nuclei, mostly hydrogen and helium with trace amounts of lithium. And then the universe cooled and expanded, and the era of primordial nucleosynthesis came to an end. And all the hydrogen that would ever exist without stellar help had been made. And some of that hydrogen, over the billions of years that followed, ended up in you, in the cup of tea you drank earlier, in the cells of your body, in the water that is even now flowing through your bloodstream. And that water, the water molecules specifically, have their own history, because water is constantly cycling through the Earth system, evaporating and condensing, flowing through rivers and oceans and underground aquifers, being taken up by plants and animals and released again. And this cycling has been going on for billions of years, which means that the water in your body at this moment has been many other things before it was you. Some of the water molecules in your body almost certainly passed through dinosaurs, through the massive sauropods that drank from Jurassic rivers, through the tyrannosaurs and triceratops of the Cretaceous, because water does not disappear, it merely moves. And there has been roughly the same amount of water on Earth for billions of years, cycling endlessly through rock and air and living things, and you are simply the current location of some of that water. A temporary arrangement that will eventually release those molecules back into the cycle for something else to use. Some of the water in you flowed through ancient oceans, oceans that existed before any animal had eyes, before the first fish, before the first cells with nuclei, oceans that were home to nothing but bacteria and archaea, simple single-celled organisms that would eventually give rise to everything complex and multicellular fossil, including you. And the water that flowed through those primordial seas is the same water, in a molecular sense, that is now part of your body, that is now helping to maintain your blood pressure and regulate your temperature and carry nutrients to your cells as you lie there breathing slowly. Let us think also about your carbon, because carbon is the backbone of organic chemistry, the element around which the molecules of life are built, and you contain rather a lot of it, enough carbon in fact to make approximately 9,000 pencils. If someone were to extract it from you and press it into that familiar form, which hopefully no one will, but it gives you a sense of the quantity involved. 9,000 pencils worth of carbon atoms, each of those carbon atoms forged in the heart of a star, fused from helium nuclei in a process that occurs at temperatures of hundreds of millions of degrees, and then ejected into space when that star ended its life, and then gathered into our solar system and our planet, and eventually into the food you have eaten and the cells you have built from that food. And you contain iron that was made in the final moments of massive stars, in the violence of supernova explosions. And there is enough iron in your body to make a small nail, about 3 inches long. And this iron is mostly found in your blood, in the hemoglobin molecules that carry oxygen from your lungs to your tissues. So, the iron forged in dying stars is now essential to the process by which you breathe, by which you stay alive, by which you listen to these words and feel yourself growing heavier with approaching sleep. The physicist Lawrence Krauss once noted that the atoms in your left hand probably came from a different star than your right hand, which is a rather lovely thought to carry with you into sleep. The idea that you are an assembly of materials from multiple sources, multiple stellar furnaces scattered across the galaxy, brought together by gravity and chemistry and biology into the specific configuration that is you, listening to this, breathing slowly, feeling the weight of your limbs against the bed. And all of these atoms, the oxygen and the hydrogen and the carbon and the iron, all the atoms that compose you, are themselves evidence of something physicists cannot fully explain, something we have been discussing throughout this narration, the mystery of why matter exists at all, the cosmic asymmetry that allowed particles to outnumber antiparticles in the early universe, the tiny imbalance that left something behind when almost everything annihilated. You are made of the winning side of a contest that physics cannot yet understand. You are composed of the matter that survived, the particles that remained when the great annihilation was finished. And every atom in your body carries this mystery within it, not as something you need to solve or even think about very much, but simply as a fact about what you are. A deep truth about your existence that requires nothing from you except perhaps a moment of quiet wonder as you drift towards sleep. The atoms in your body have been on a very long journey to reach you, a journey of billions of years through space and time, through stellar cores and interstellar clouds and planetary surfaces and countless other living things. And now here they are, arranged into the particular pattern that thinks of itself as you, that has preferences and memories and a voice inside its head that is listening to these words. And soon, those atoms will rest, will participate in the quiet maintenance of a sleeping body, and the mystery of their existence will continue unresolved, but also untroubling, simply part of what it means to be a thing made of matter in a universe where matter should perhaps not exist, but does. And you are proof of that. You are evidence. You are the unlikely outcome, resting in the dark and breathing slowly and letting go of the day. And so we come now to the largest view of all, the widest lens through which we might consider this strange fact of existence, this peculiar circumstance in which you find yourself drifting towards sleep inside a body made of matter that, by all the careful accounting of physics, should never have come to be. Let us zoom outward together, gently and without haste, from the small warmth of wherever you are resting tonight, outward past the curve of the Earth, past the patient orbit of the Moon, past the other worlds that circle our modest star, outward still through the scattered ice and rock at the edge of our solar system, and then farther, much farther, into the vast and quiet dark between the stars. The observable universe, which is to say, the portion of everything that light has had time to reach us from since the beginning, contains approximately 10 to the 80th power atoms. That is a 1 followed by 80 zeros, a number so large that it defeats any attempt at intuitive understanding. And yet, it is also a number that can be written down on a single line, held in a single thought, considered in a single sleepy moment before consciousness drifts away. 10 to the 80th power atoms, each one a tiny arrangement of quarks and electrons, each one bound together by forces that emerged in the first fractions of a second after the universe began, each one representing a small victory of matter over antimatter in a contest that should have ended in a draw. Every single atom in the observable universe, without exception, is matter that the fundamental symmetries of physics did not predict. Matter that exists only because something, somewhere, at some point in the earliest moments of cosmic history, tipped the scales by the smallest possible margin. In the year 2004, astronomers pointed the Hubble Space Telescope at a tiny patch of sky, a region so small that it could be covered by a grain of sand held at arm's length, a seemingly empty corner of the heavens in the constellation Fornax, where very little appeared to exist. They kept the telescope pointed at this unremarkable darkness for a very long time, allowing the ancient light from the most distant objects to accumulate slowly on the detector, photon by patient photon, over the course of many months of observation spread across several years. What emerged from this patient-looking was an image called the Hubble Ultra Deep Field, and it revealed something that still carries a gentle weight of wonder for anyone who pauses to consider it. In that tiny patch of apparent emptiness, that grain of sand-sized window into the cosmos, the telescope found approximately 10,000 galaxies. 10,000 galaxies, each one a vast collection of hundreds of billions of stars, each star potentially hosting its own system of planets, each planet made of atoms that trace their origin back to the same unexplained asymmetry we have been discussing. The light from the most distant of these galaxies had been traveling toward us for over 13 billion years, which means that we were seeing them as they appeared when the universe was still young, when the first generations of stars were just beginning to forge heavier elements in their cores, when the cosmic story was still in its opening chapters, and all of it, every spiral arm and every elliptical haze and every tiny smudge of light that represents an entire island universe. All of it exists because matter won its inexplicable victory over antimatter in the first moments after the Big Bang. More recently, in December of 2021, a new telescope was launched from Earth, folded carefully inside a rocket and sent on a journey of about 1 million miles to a special point in space where the gravitational influences of the Earth and Sun create a kind of stable parking spot for spacecraft. This was the James Webb Space Telescopes, and after it arrived at its destination and slowly unfolded its golden mirrors and its tennis court-sized sunshield, it began to look even deeper into the cosmos than Hubble ever could. The James Webb Space Telescope sees primarily in infrared light, which allows it to detect the stretched and reddened glow of the most ancient galaxies, objects so distant that the expansion of the universe has shifted their light far beyond what human eyes can perceive. In its early observations, released to the public beginning in 2022. This new telescope showed us galaxies that existed perhaps 400 million years after the Big Bang, structures of stars and gas and dust that were already forming when the universe was only about 3% of its current age. And here too, in these most ancient visible structures, we find the same mystery, the same unexplained gift. The matter that makes up those primordial galaxies, the hydrogen and helium that had begun to collapse into the first stars, the traces of heavier elements that were already being forged and scattered into space, all of it represents the survival of something that should have been annihilated. When we look at the deep field images, whether from Hubble or Webb or any of the other instruments humanity has built to extend our vision into the cosmos, we are looking at 10,000 or 100,000 or 1,000,000 separate instances of the same fundamental puzzle, the same gentle enigma. Each galaxy, a vast cathedral of matter that exists without a fully satisfying explanation for why it exists at all. Every star you might see if you stepped outside tonight and looked up at a clear sky is burning because matter exists. Every planet orbiting those stars, from scorched rocks huddled close to their parent suns to frozen worlds drifting in the outer dark, is assembled from atoms that the physics we understand did not anticipate. Every moon, every asteroid, every comet trailing its long tail of sublimating ice, every ring system and every cloud band and every storm swirling in the atmosphere of every giant planet, in every solar system, in every galaxy in the observable universe. All of it is made of the same unexplained surplus. The mystery is not confined to some exotic corner of reality, not tucked away in some rare or unusual phenomenon that only specialists need to consider. The mystery is the very fabric of everything, woven into the basic fact that there is something here at all. Something rather than the nothing that perfect symmetry would have produced. On February 14th of 1990, the Voyager 1 spacecraft, which had been launched 13 years earlier and had already completed its primary mission of exploring Jupiter and Saturn, received a command from Earth to turn its camera around and take one last set of photographs before the camera was switched off forever to conserve power. The spacecraft was at that point about 3.7 billion miles from home, far beyond the orbit of Neptune, drifting outward into the space between the stars. From that immense distance, it photographed the planets of our solar system, creating a kind of family portrait of the worlds that orbit our sun. In one of those images, Earth appeared as a tiny point of light, less than a single pixel in size, suspended in a scattered ray of sunlight that happened to cross the frame. The astronomer Carl Sagan, who had advocated for taking this photograph, later reflected on what it meant to see our entire world reduced to such a small and fragile-looking mote. That pale blue dot, as the image came to be known, shows everything that has ever happened in human history. Every birth and every death, every war and every peace, every act of kindness and every act of cruelty, every book written and every song sung and every quiet moment of someone drifting off to sleep. All of it took place on a tiny grain of matter suspended in a sunbeam, a grain that is itself part of the vast unexplained surplus we have been discussing. You are lying somewhere on that dot right now. Or rather, you were on that dot when the photograph was taken, and you are on it still. And the dot itself is made of atoms that physics cannot fully account for. The planet beneath you, the air you are breathing, the warmth of whatever covers you as you rest, the gentle weight of your own body settling into stillness. All of it is composed of matter that represents a cosmic preference for something over nothing, a preference so slight that it amounts to roughly one extra particle of matter for every billion particle-antiparticle pairs that were created and destroyed in the early universe. 1 in a billion is a very small preference. If you tried to represent it visually, you might imagine a vast auditorium filled with 1 billion people arranged in pairs. And then you would add one single person standing alone at the edge of the crowd, without a partner, surviving when all the pairs had cancelled each other out. That one remaining person, in this admittedly imperfect analogy, represents all the matter in the observable universe, all the galaxies and stars and planets, all the mountains and oceans, all the living things that have ever existed on any world, anywhere in the cosmos, all the atoms in your body as you lie here, drifting towards sleep. Everything that exists is the residue of an almost perfectly balanced equation that came out slightly, inexplicably, beautifully unbalanced. We do not know why this happened. We have hypotheses, and they are careful and mathematically sophisticated and interesting to consider. But none of them has yet been confirmed by experiment. None of them has been elevated to the status of settled knowledge. The mystery remains open, which means that in some sense you are falling asleep inside an open question, resting in a universe that has not yet finished explaining itself. But there is something gentle about this, something that need not trouble the mind as it softens towards unconsciousness. The fact that we do not know why the universe preferred matter over antimatter does not make your existence any less real or any less restful. The atoms in your body do not require an explanation in order to continue being atoms. The warmth of your bed does not depend on resolving fundamental puzzles in particle physics. You can let the mystery be present without needing to solve it, the way you might let starlight be present without needing to count every star. And starlight is perhaps a fitting final image, because when you see the light from a distant star, you are seeing photons that were emitted by matter that should not exist, traveling across the void to be absorbed by other matter that should not exist, namely the cells in your eyes that convert light into the experience of seeing. The whole transaction, from the nuclear fusion in a stellar core to the quiet recognition of a point of light in a night sky, is a transaction between different portions of the universe's unexplained surplus, different fragments of the matter that survived the great annihilation. Every photon of starlight that has ever reached Earth is a message from one impossible thing to another, a gentle hello from across the cosmic dark. You are drifting to sleep inside this vast and improbable situation, carried on atoms that physics says should never have been, resting on a planet that orbits a star that burns because matter exists, in a galaxy that is one of trillions, all of them equally unexplained, all of them equally present. The mystery settles over you like starlight itself, which is to say gently, warmly, without demanding anything of you. It is simply there, this beautiful unsolved question at the heart of everything, and you are part of it, made of it, held within it as you let go of waking and slip into whatever quiet the night has to offer. The universe, for reasons still unknown, preferred something over nothing by the smallest possible margin. And you exist because of that preference, as does everything you have ever touched or loved or seen. There is nothing more required of you tonight than to rest inside this fact, to let your breathing slow, to let your thoughts grow soft and indistinct, to allow yourself to be what you are, which is a temporary and precious arrangement of matter that the cosmos, for its own mysterious reasons, allowed to be. Sleep well, impossible thing. Sleep well, child of the asymmetry. The atoms will still be here in the morning, just as unexplained, just as warm, just as gently and stubbornly real.